Breaking news tonight is quantum AI scans have confirmed that interstellar object 3I/Atlas is not natural at all. NASA didn't expect this. Buried in the latest data is something so bizarre it's forcing scientists to rewrite what they thought they knew about the universe. The culprit 3 Atlas, an interstellar relic older than our solar system itself. For weeks it slipped past detection systems, almost lost forever. Scientists are calling it a cosmic alarm bell, a warning written across the sky. But what is Atlas really? A relic from before the Earth was born, or a messenger of something we don't yet understand? The ancient molecule vault. The age of 3I Atlas fundamentally changes how we interpret everything about this visitor. At an estimated 7 billion years, this comet predates our entire solar system by roughly 3 billion years. It formed when the Milky Way galaxy was dramatically different, with higher star formation rates, different chemical abundances, and environmental conditions we can only model theoretically. The trajectory analysis that suggests this extreme age traces 3I Atlas back to the galaxy's thick disk, a stellar population representing some of the oldest structures in our cosmic neighborhood. This ancient region operated under physical and chemical conditions that no longer exist anywhere in the modern galaxy. Yet somehow, this cosmic fossil has preserved volatile materials like carbon dioxide and water that should have been lost to space eons ago. The James Webb Space Telescope detected the highest ratio of carbon dioxide to water ever observed in any comet. This preservation over such vast timescales suggests either extraordinary storage mechanisms or chemical stability under extreme conditions that we don't understand. The radiation exposure implications are staggering. 7 billion years of cosmic ray bombardment should have fundamentally altered any organic compound in the comet's structure. The fact that complex molecules remain detectable indicates either exceptional shielding properties or chemical processes that maintain molecular integrity over cosmic timescale. The thermal evolution of 3E Atlas over billions of years presents additional puzzles. Most theoretical models predict that ancient comets should gradually lose their volatile components through sublimation during passages near stars or heating from radioactive decay. Yet 3I Atlas has maintained sufficient volatile content to become active when heated by our Sun, suggesting internal thermal properties or structural arrangements that resist normal evolutionary processes. The preservation mechanisms required to maintain such chemical complexity over galactic timescales challenge our understanding of material behavior in deep space environments. Either the comet spent most of its existence in extraordinarily cold stable conditions, or it possesses internal characteristics that actively protect volatile compounds from degradation. Luis Salazar Manzano from the University of Michigan discovered that 3I Atlas shows severe carbon chain depletion containing significantly fewer C2 and C3 molecules than any other comet ever studied. This depletion pattern doesn't match what we'd expect from objects that spent billions of years traveling through interstellar space, where these carbon chains should gradually accumulate. The classification crisis. The initial misidentification of 3I Atlas as asteroid A11PL3Z reveals fundamental problems with automated detection systems that could have cost us one of the most significant astronomical discoveries in decades. Our algorithms are optimized to recognize objects that behave like the millions of rocks and iceballs we already know about in our local neighborhood. The Atlas survey system in Chile, despite being one of our most sophisticated detection programs, initially processed 3 Atlas according to standard asteroid classification criteria. The object's unusual characteristics, lack of expected chemical signatures, anomalous thermal properties, and non-standard activity patterns were initially interpreted as measurement noise rather than genuine anomalies. This classification error highlights a deeper problem with machine learning approaches to astronomical discovery. Training algorithms on local solar system objects creates inherent biases that can blind us to genuinely exotic phenomena. When something operates according to different physical principles, our automated systems struggle to recognize it as scientifically valuable rather than instrumental error. The human intervention that eventually recognized 3I Atlas as an interstellar comet required expertise in orbital mechanics, spectroscopy, and comparative planetology. This specialized knowledge isn't easily encoded into automated systems, creating dependency on human analysts for identifying the most scientifically significant discoveries. Similar classification problems likely affect other detection networks worldwide. The Catalina Sky Survey, Linear, and NEOS programs all use similar algorithmic approaches that prioritize objects matching known patterns. Genuinely anomalous objects might be systematically filtered out before human experts ever see them. The comparative analysis with previous interstellar visitors reveals important patterns in detection challenges. 1. IUMA was initially classified as an asteroid before showing comet-like acceleration, while 2. Boris was immediately recognized as a comet due to its obvious coma and tail. 3. Atlas represents an intermediate case. Clearly active like 2 Boris, but with chemical signatures so unusual that automated systems couldn't properly categorize it. Molecular cocktail rewriting formation theory. The James Webb Space Telescope's detailed analysis of 3E Atlas has revealed a chemical composition so unusual that it challenges fundamental theories about how comets form around other stars. The infrared observations detected not just the record-breaking carbon dioxide abundance, but also water ice, carbon monoxide, and carbonyl sulfide, creating a molecular signature unlike anything in our solar system's comet population. The presence of carbonyl sulfide is particularly intriguing because this compound requires specific temperature and pressure conditions to form and remain stable. Finding it alongside such extreme carbon dioxide concentrations suggests formation environments with chemical processes we don't fully understand. The molecule's detection implies that 3I Atlas either formed in a region with unusual sulfur chemistry or underwent processing during its interstellar journey that created these compounds. The carbon monoxide detection adds another layer to the chemical puzzle. While carbon monoxide is known from other comets, its abundance relative to water and carbon dioxide in 3I Atlas doesn't match standard models of ice condensation in protoplanetary disks. The ratios suggest either formation at temperatures much lower than typical comet formation regions or exposure to radiation environments that selectively process certain molecules. What makes these findings even more remarkable is how they've been preserved over billions of years of interstellar travel. Carbonyl sulfide is particularly fragile and should decompose under cosmic ray bombardment. Yet, it remains detectable in the comet's coma. This preservation suggests either extraordinary protection mechanisms or chemical regeneration processes operating within the comet's interior. Iceline formation mystery. The extreme chemical composition of 3 Atlas has led scientists to propose that it formed near what's called the carbon dioxide iceline in its original protoplanetary disk. This represents a specific distance from its parent star, where temperatures drop just low enough for carbon dioxide to transition from gas to solid ice, creating a zone of enhanced carbon dioxide accumulation. Formation at the carbon dioxide iceline would explain the record-breaking abundance ratios observed in 3I Atlas. But it also raises questions about the disk conditions around its parent star. Most protoplanetary disk models predict that the carbon dioxide iceline should be relatively close to the central star in regions where water would still be gaseous. Yet 3-2 Atlas clearly contains substantial water ice alongside its carbon dioxide. This suggests either a more complex disk structure than our models predict or formation conditions involving temperature gradients and chemical processes that operated differently around the comet's parent star. The disk might have experienced rapid cooling events or unusual opacity variations that created multiple icelines at different distances, allowing for the co-condensation of water and carbon dioxide. The preservation of these formation signatures over 7 billion years provides an unprecedented window into early disk chemistry around other stars. Most planetary formation theories are based on observations of young disks and models of our own solar system's early history. 3 Atlas represents direct physical evidence of how planet formation processes actually operated in the ancient galaxy. Global observatory fights. The limited observation window for 3 Atlas has triggered what amounts to an astronomical gold rush among research institutions worldwide. Unlike normal space discoveries that can be studied for years or decades, this ancient visitor provides maybe 6 months of decent observation time before it vanishes back into the cosmic void forever. The competition for James Webb Space Telescope time has gotten particularly intense. Research teams are essentially fighting over hours of observation time on humanity's most expensive scientific instrument. NASA, ESA, and universities are all submitting proposals that basically say this might be the most important comet ever discovered. So, give us your best telescope. But Webb can only look at one thing at a time. And everyone wants their piece of this cosmic mystery. European countries are having their own internal drama about who gets to use which telescopes when. France has military satellites that could track 3I Atlas in ways civilian telescopes can't. But sharing the data means revealing capabilities they normally keep secret. Germany's got some of the world's best ground-based telescope networks, but they're already booked solid with other research projects. Italy is worried that all this extra telescope activity is going to interfere with their commercial satellite operation. China is doing their own thing entirely, which is both helpful and frustrating for Western scientists. Chinese astronomers have access to unique observation capabilities and are definitely studying 3 Atlas, but the political tensions mean they're not sharing much data. So, we've got parallel research happening on the same object with different teams potentially reaching different conclusions about the same phenomena. Private space companies find themselves in weird positions, too. SpaceX technically has the rocket power to launch observation missions faster than most government space agencies, but they can't just decide to study an interstellar comet on their own. They need government contracts, international agreements, and scientific partnerships that take months to arrange. Time we don't have. The December 2025 deadline is driving everyone slightly crazy because this represents humanity's last chance to study this particular cosmic time capsule. Missed this opportunity, and we're waiting millions of years for the next one. Space security has major blind spots. The 3I Atlas discovery exposed some pretty embarrassing gaps in our space monitoring systems. Basically, we built our entire detection network around finding things that act like the space rocks we already know about. When something shows up that plays by different rules, our systems almost miss it completely. The problem is like training a security camera system to spot suspicious activity by showing it thousands of videos of normal human behavior. It gets really good at flagging people walking in an unusual way or carrying strange objects. But if a robot walks through the parking lot, the system might not even recognize it as worth paying attention to because it doesn't match any human behavior patterns. Our asteroid detection programs work the same way. They're scanning the sky looking for objects that move at predictable speeds, reflect sunlight in familiar ways, and follow gravitational laws. We understand 3 Atlas was doing all of that, but also glowing green through impossible chemistry and ejecting dust in directions that violate basic physics. The Atlas system in Chile almost categorized this discovery as measurement error because the spectroscopic data didn't make sense. If the human analysts hadn't been particularly curious about this asteroid designation, we might have missed one of the most scientifically valuable objects ever detected. The Vera Rubin Observatory that's being built could help with this problem. It's designed to photograph the entire visible sky every few nights, which means it might catch weird objects earlier when we have more time to study them. But even Rubin is programmed to look for specific types of changes and movements. Space-based telescopes like the proposed NEO Surveyor could detect heat signatures from objects that are generating their own energy like 3 Atlas apparently does. But these missions are still in development and they're focused on finding potentially dangerous asteroids rather than scientifically interesting visitors from other star systems. The real issue is that we need detection systems smart enough to recognize when something genuinely unusual is happening rather than just filtering out anything that doesn't match known patterns. That requires a complete rethink of how we scan space for interesting objects. The dust analysis. The detailed study of dust particles ejected by 3I Atlas has revealed internal structural characteristics that challenge our understanding of how ancient comets maintain cohesion over cosmic timescales. The particles measured at hundreds of microns across are significantly larger than typical comet dust and suggest binding mechanisms or material properties unknown in our solar system's population. High-resolution imaging from the Hubble Space Telescope has shown that these large particles maintain relatively uniform compositions despite their size, indicating either homogeneous internal structure or chemical processes that create consistent material properties throughout the comet's interior. This uniformity is unusual for objects that formed through accretion of diverse materials in protoplanetary disks. The slow ejection velocity of approximately 1 meter per second suggests that the comet's surface materials have unusually strong binding forces compared to typical ice-dust mixtures found in solar system comets. This could indicate either different formation processes that created more cohesive structures or chemical changes during the comet's billion-year interstellar journey that strengthened material bonds. Spectroscopic analysis of individual dust particles shows chemical signatures that match the bulk composition detected in the comet's coma, but with concentration gradients that suggest layered internal structure. These gradients might preserve information about different formation epochs or environmental conditions encountered during the comet's galactic orbit. The particle size distribution also provides insights into the comet's thermal evolution. Large particles typically indicate either low-energy ejection processes or materials that resist fragmentation under thermal stress. Both possibilities suggest internal properties that differ significantly from conventional comet models based on solar system objects. The chemistry mystery. The Greenblow paradox of 3 Atlas isn't just a curious anomaly. It's potentially overturning decades of established spectroscopic science. Every astronomy textbook says that dicarbon molecules create green light in comet atmospheres. But 3 Atlas is blazing green without any detectable dicarbon, which is like finding a car engine running perfectly without any pistons. This discovery forces uncomfortable questions about how much we actually understand about molecular physics in space environments. Our spectroscopic analysis depends on reference libraries built from studying materials in our own solar system. When those libraries prove inadequate for analyzing visitors from other star systems, we're essentially flying blind. The complete absence of expected carbon chain molecules suggests either formation conditions so exotic that they don't exist anywhere in our local neighborhood or chemical processes operating during the comet's billion-year journey that we haven't even theorized about yet. Either possibility means our understanding of interstellar chemistry is seriously incomplete. The presence of nickel compounds adds another wrinkle to this puzzle. Nickel typically requires high-energy formation environments or intense radiation exposure to become incorporated into icy materials. Finding it in a comet suggests either formation near a much more active star than our Sun or encounters with radiation environments during interstellar travel that fundamentally altered the object's chemistry. The detection of cyanogen alongside the absence of other carbon chains creates a chemical signature that doesn't match any formation or evolution models in our databases. It's like finding all the ingredients for a complex recipe except for the main component, yet somehow still ending up with the finished dish. Traditional spectroscopic interpretation assumes we're analyzing materials that formed under conditions similar to our solar system's early history. 3 Atlas is teaching us that this assumption might be dangerously naive when dealing with objects from other star systems or different epochs of galactic evolution. The galactic context. The thick disk origin of 3I Atlas places this comet in a galactic context that fundamentally changes how we interpret its characteristics and significance. The thick disk represents a stellar population that formed when our galaxy was much younger with different metallicity levels, star formation rates and chemical enrichment processes than the thin disk region where our solar system later developed. Objects from the thick disk carry chemical signatures from an era of galactic evolution that we can only study through computer simulations and stellar archaeology. 3I Atlas provides direct physical samples of materials that formed under those ancient conditions, offering unprecedented insights into how planetary systems developed during the early epochs of our galaxy. The orbital mechanics implications of a thick disk origin are equally remarkable. For 3I Atlas to have survived the journey from that ancient stellar population to our current location requires navigating billions of years of galactic evolution, including passages through spiral arms, encounters with stellar clusters, and gravitational perturbations from massive objects like molecular clouds and supermassive black holes. The preservation of volatile materials during such an extensive galactic odyssey suggests either extraordinary storage conditions or internal characteristics that resist the normal processes of chemical evolution in interstellar environments. The comet has essentially served as a time capsule maintaining ancient chemistry through cosmic scale journeys that should have erased all traces of its original composition. The trajectory analysis that revealed the thick disk origin also provides information about the comet's orbital history within our galaxy. Computer models suggest that 3I Atlas has likely completed multiple galactic orbits, taking roughly 200 million years per circuit around the Milky Way's center. Each orbit would have exposed the comet to varying radiation environments, gravitational fields, and interstellar medium conditions. December Showdown. December 2025 isn't just another month on the calendar for astronomers worldwide. It's when 3I Atlas makes its closest approach to Earth. And it might be the most scientifically important few weeks in modern space science. This cosmic time capsule will never be this close again. Which means we have one shot to solve mysteries that could revolutionize our understanding of how planets form around other stars. Ground-based telescopes will finally get the resolution they need to directly photograph the comet's nucleus and maybe even spot surface features that explain its bizarre behavior. We're talking about imaging something that's been traveling through space since before Earth existed, potentially revealing structural details that clarify how materials from the early galaxy maintain their integrity over such mind-boggling timescale. The James Webb Space Telescope has carved out dedicated observation slots to study molecular emissions that are completely invisible to ground-based instruments. These infrared observations could finally crack the green-glow mystery by detecting trace compounds that have been hiding at wavelengths we can't access from Earth's surface. Radio telescope arrays worldwide are preparing for something that sounds like science fiction, but is totally serious. Listening for any electromagnetic signatures that might indicate this ancient visitor isn't entirely natural. While most scientists consider artificial origins extremely unlikely, the unprecedented chemistry of 3E Atlas justifies checking every possible explanation for its anomalous behavior. International observation campaigns are coordinating around-the-clock monitoring throughout the approach phase. Different telescope networks will hand off coverage as Earth rotates, ensuring continuous documentation of any changes in activity levels, chemical signatures, or physical characteristics that could provide crucial insights. The gravitational effects during close approach could also reveal information about the comet's internal mass distribution and density structure. These measurements might finally clarify whether the unusual properties result from exotic materials, structural arrangements we've never seen before, or processes that operated differently in the ancient galaxy. This December encounter represents the absolute final opportunity to solve the puzzle of 3I Atlas before it disappears back into interstellar space. We certainly can't wait to see how this pans out. Let us know your thoughts in the comments down below.